Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We were delivering lecture series on X-ray crystallography and solid-state chemistry. This is our 10th lecture, and mainly we will talk on X-ray diffraction in this lecture. This slide I did discuss in the 9th lecture, but I think I have to point out little more points in these slides. This is how a X-ray characteristic X-ray lines occur. That's what we are showing in the slides, and we talked about it in the 9th lecture. What I said, that an electron bombarding the target, they know that in X-ray we have a target that we were discussed in the last lecture. So when electron bombarding a target, sufficient energy is there to displace a electrons. That is principal quantum number 1 shell, a electron. And we know that a vacant place here could not be there. Immediately, then within 10 to the power minus 4 seconds, another electron from outer shell fills the vacant place, and thereby radiating X-ray, characteristic X-ray. In this case, I have been showing that if there is a transition to K shell from M or L shell, the lines creates, X-ray lines creates, I call it K lines. Similarly, if there is a knockout from L shell and a transition occurs from N shell and M shell, we create L lines. Okay. What about the M lines? Well, we should have a electron knockout from M shell and transition from N and higher shells occur M lines. Okay. What about the N lines? Do you have that? The removal of electron from N lines, when it fills up, we do see that we do not get any characteristic X-ray lines. So therefore, we are not concerned about the lines, shell beyond N. Okay. Then we go for this. This is the origin, and we now talk about the spectrum, how it looks like. Well, here we have in the y-axis intensity and the x-axis lambda, that means wavelength. What we are changing here, we are changing applied voltage. And we can see a spectrum of applied voltages. And if it's 20 kilovolt, we get it like this. With 30 kilovolt, we get it like this. And that means with increasing voltage, we get the more and more intensity. One more thing, that at certain wavelength, we do have zero intensity. So here in 20 kilovolt, we have zero intensity. We have in 30 kilovolt, we have zero intensity, and so forth, so forth, so forth. So we see that zero intensity with voltage also changes from longer wavelength to shorter wavelength if we higher the applied voltage. Okay, this is how it is. But here we do not see any characteristic peaks. All are merged. Now we see when we get characteristic peaks. Well, you see, we take this figure. Electron goes on colliding with other atoms and successively losing energy, and then all energy is spent. And that's what we see in the spectrum, and that's what we call background radiation or white radiation. And when this graph tells us this point, when this intensity is 0, the wavelength there, we call it short wavelength limit, SWL, short wavelength limit. So in all spectrum, we get short wavelength limit. Now that this spectrum, we are showing that operated at 20 kilowatt. Here, with 20 kilowatt, we do not see any characteristics X-ray spectra. It is just a white background radiation. Increasing the applied voltage, we start noticing that the characteristic lines are coming up. You see, this is characteristic lines, radiations are coming up. And that what we call the continuous radiation. That one is the continuous radiation. But here we see the peak of a characteristic radiation, that's the transition, what is said from L shell to K shell. And this is this is K alpha and this is K beta. Well, these K beta and K alpha are single peak, but when we talk more about it, going to higher potential difference and see what happens in later slides. But then now we have to also talk about absorption. We know very well that X-ray absorb a certain extent by materials, solid materials. We talked about when we were talking about the X-ray tube, that we have to have window with light metal so that X-ray does not absorb so much. We also said that we have to have shielding with heavy metal so that X-ray doesn't come out, it absorbs. So we see that intensity will be reducing when material absorbed X-ray. Okay, this can be also said that intensity of transmitted X-ray beam is related to the original intensity. How it is related? It is related. Intensity of the transmitted beam is equal to intensity of the original beam e to the power mu x. What is mu? Mu is the linear absorption coefficient of material. What is x then? X is the thickness of the material. The value of mu depends on the solid materials, which materials we are talking about. Not only this, the material and which state of the material is all we are talking about. Is it solid or it is liquid or gas? So that means mu is dependent on the number of atoms the X-ray traversed by the beam. Okay, so this is also a point we have to overcome, because depending on solid, liquid, and gas, the linear absorption coefficient is dependent. Therefore, it has been confirmed that mu by density of the material is constant regardless of its state. So this mu by density is called mass absorption coefficient, mu m, mass absorption coefficient. So we can rewrite this equation to I is equal to I naught E minus mu m rho and x. And then if we plot this, that mu m versus wavelength, we get that generally absorption generally increases with increasing wavelength. That means if the wavelength is greater, the absorption is also greater, and this generally increases like this. But then we see some discontinuity in this graph. Here is mass absorption coefficient, here wavelength in angstrom. So we just see a discontinuity. Here is a discontinuity, and also here is a discontinuity. And this discontinuity, we call it absorption age. So this is K absorption age, this is L absorption ages. Okay. Well, this is a mass mass absorption coefficient versus wavelength, and this curve is for tungsten material. So we can see that a Ka edge absorption age is 0.178 angstrom. This means that X-ray of this wavelength have sufficient energy to knock out electron from K shells. Okay. Another point we have to see that we are talking about here K absorption age, L absorption, etc. What about M absorption age and N absorption ages? If we continue this graph with higher wavelength, we will notice also the discontinuities for M and N shell, and that's what we call M and N ages. But in crystallography, we do not use this. We only use K absorption age to talk about absorption and see what we will use for it. Okay, this what we are talking about. This is a copper spectrum. This is a copper spectrum. Here you can see that we distinguish the K beta and then K alpha and K alpha 2. Now, if we need to have a monochromatic X-ray, we do need for all experiments, almost all experiments, monochromatic X-ray. That means we cannot have K beta 1, K alpha 1, K alpha 2, and all this white background to use as a source of X-ray to characterize our materials. What we need then, we need to have a monochromatic line, a single X-ray beam. So for that, we have to use some materials which will absorb, let's say, K beta, and some of the background or white radiation. We see here is a dotted line. This is the absorption curve of nickel. Absorption curve, mass absorption curve of nickel. We can see that nickel has an absorption age, K absorption age, which is 1.48 angstrom. A bit longer than K beta. Here is the K beta, wavelength of K beta, and we see that nickel has an absorption age of 1.48, a bit longer than K beta, copper K beta 1. Therefore, if we have a foil, thin foil of nickel, and that source where X-rays are passing, we will absorb the K beta 1, total K beta 1, you can see, we can absorb the total K beta 1 plus a lot of background radiation or white radiation, thereby having only K alpha, both K alpha 1 and K alpha 2. Okay? If both K alpha 1, K alpha 2. And you can see the difference in wavelength in K alpha 1 and K alpha 2 are very little, sufficiently close wavelengths. So in crystallography, many crystallography application, this K alpha 1 and K alpha 2 used as a single wavelength. And but after this, in many applications we do use on K alpha, both alpha 1 alpha 2 as one single radiation, same wavelength. But we also see that there are other crystallographic applications, for example, quantitative powder diffraction analysis or single crystal analysis. We even require more strictly monochromatic radiation. That means only one of the radiation. So we have to have only one of the radiation, not K alpha 1, not K alpha 2. It is only either K alpha 1 or K alpha 2. This is what is called, we call strictly monochromatic radiation. How do we get? Here you see that with nickel foil, we can absorb K beta 1, but we cannot absorb one of these also. So therefore, we have to have a mechanism by which we can get another or K alpha 1 or K alpha 2, one of these to be absorbed. And only we get single wavelength radiation. So for this application, crystal monochromator, we use crystal monochromator also. Usually a large single crystal of quartz is used to get only K alpha radiation for copper X-ray spectrum from. So not only nickel foil, but also we have to use the single crystal of quartz to get one radiation, single radiation, and that is copper K alpha radiation. Why you use copper K alpha radiation? You can see the copper K alpha radiation is much intense than both K alpha 2 and K beta. Therefore, we want to have this radiation for a strictly monochromatic radiation and use this in very many determination of structure of order of single crystal and even the amorphous materials. Okay, now we are talking about only copper acceleration, but we do have other target material. We could have molybdenum, we could have copper, nickel, cobalt, iron, chromium. And that is, we have to specify which target we want to have. And this depends on what are the applications, or what are the analysis we have to do. In many powdered analysis, we see that only copper and molybdenum are being used, rest very little. Similarly, for single crystal work, we see that we are using molybdenum. Okay, now that we see that what are the wavelength with that. See, this is the atomic number of this element. Atomic number molybdenum is 42, 29, 20, 27, 26, 24. You see, with higher atomic number, the wavelength of X-ray decreases, shorter wavelength. You get shorter and shorter wavelength. You see, copper 24 gives us K alpha 1, 2.28962 angstrom, whereas molybdenum alpha 1 gives us 0.70926 angstrom. So this again, that which sort of radiation with what wavelength we need to have for our research or for our purposes. So we decide them that way, and we also order from the market target material of that one. Okay, you see, here we are seeing the peak height at kilovolt. So if we have 18 kilovolt, 80 kilovolt, 50 kilovolt, 50, 45, 40, 35. So we can see that if we have to have X-ray, that applied voltage must have to, characteristic X-ray line, applied voltage must have to above 35 or so. So for copper, what we are using around applied at 40 to 50 and 20 milliampere will be the parameter we will use for our X-ray generator, and then get this radiation we want. And for copper, we use a nickel to get rid of beta and white radiation. Similarly, if we want to have molybdenum, we have to have zirconium, and this is the absorption age. So we need to have zirconium to filter cobalt K beta 1, you see, zirconium. Similarly, depending on K beta 1 values, which sort of element we have to use for absorption, that is there. For copper, it is vanadium, chromium, vanadium, iron, it is manganese. For cobalt, it is iron. For nickel, it is cobalt. And for copper, it is nickel. And for molybdenum, we use zirconium. Okay. Here is another thing that what we talked about, that in many cases, we use K alpha 1 and K alpha 2 together. And then this is the average of the K alpha. This is the wavelength we use when we are talking about chromium, or we are talking about iron, we are talking about copper, talking about molybdenum. Very recently, we do get target material with silver. And there you see that silver is higher at atomic number than that of molybdenum, and therefore we get still a shorter wavelength of X-ray. And then this is the filter we'll use for this material. We talked about it. Okay. Then we go. Now, let us take some problem and discuss a little bit of it. Well, we are given a spectrum like this, and we are asked to put an X-ray spectrum of iron target. This is an X-ray spectrum of iron target. We are asked to label the spectrum fully. What to do then? How we would label it? You know, in any spectrum like this, we have to first identify what is in X-axis and what is in Y-axis then. Okay? So we know in X-axis, it is wavelength. And for this X-ray spectrum, Y-axis is the intensity. So first of all, we have to draw an X-axis and then an Y-axis here. And Y-axis value is given here. It is an arbitrary intensity unit. And then there it is the wavelength, 1 angstrom, 2 angstrom, etc. Okay. So we are talking about this problem, saying that as a spectrum of a target has been given, and we are asked to label it up. Well, as I said, that we take X-axis and Y-axis, and then identify what is X-axis, what value for X-axis, and what for Y-axis, and then start identifying the peak. Well, up to this, we stop here, and we finish our 10th lecture. We will continue from this slide for the 11th lecture. Thank you very much. Thank you for your patience and patience.